Good morning everyone, welcome back to my channel. My name is Marina Matic, and today, as you can see from the title, we have another celestial navigation lecture with a warning. Today we're going to cover trigonometry basics. Let me just get this out of the way. So, trigonometry basics. I already left a message in the comments on the right, as you can see. This is not going to be easy, what we're going to do today, and you as a person, as a mariner, as whatever you are calling yourself, you have, unfortunately, you have two options. You can either try to understand this any way possible, so you don't have to just watch my videos. You can also try to learn from other educational materials. You can read books and similar things to understand what we are doing in navigation actually. Or the option number two is just take the formula, solve the formula without understanding actually what you are doing, and just get the numbers, pass the exam, and forget about everything until you reach another exam that will require you to go back to formula and learning how to do the formula. If the exam you are taking that is with celestial navigation is the last one, so you are counting that this is my master's exam, master upgrade exam, final exam, then that approach of, okay, I'm going to just learn this for this course, for this exam, could work. It's not something I recommend, but it could work. But if that is not going to be your last exam, if you know already that in 6 months, 1 year or 2 years you're going to need this again, then I prefer the first approach, you understanding what you are doing and you understanding what needs to be done. So I will have how to say, I'll be perfectly okay if I lose you today. So I understand completely this is going to be a very hard subject for you to cover, especially if during elementary school, high school, you didn't have opportunity to learn mathematics and trigonometry in a way that it's supposed to be conveyed to another person, to another student. Mathematics have, unfortunately, two options. You can have a teacher that actually knows mathematics and also knows how to transfer that knowledge, and then you have option number two. You have somebody who knows mathematics but doesn't have the skill to transfer that knowledge effectively. And once again, unfortunately, in most cases we have the option number two. We have people who are good in mathematics but they do not know how to transfer that knowledge to children, and as a result of that they grow up believing that mathematics is something hard, mathematics is something impossible. Even in my maritime college in Split, there is unspoken rule that once you pass mathematics you pass the college, so that's it. So all the other courses are more or less easy to go through, but mathematics is the hardest one. And I know this because in my class there were 40 of us, only 30 or 30, well, not only, no, only only 5 or 8 people actually passed the college, finished the college completely, got their degree, and 32 or 34 students from my class, they never finished college because of mathematics. They left mathematics for as a last exam and they never passed it. So I always suggest to students going on the first year of college to focus on the mathematics. Forget everything else, focus on the mathematics, learn it, understand it. Once you understand it and you know what you are doing and why you are doing something, it's going to be much easier for you to learn all the other things, because everything else, terrestrial navigation, celestial navigation, electronic navigation, stability, everything has foundation in mathematics, especially trigonometry. So let me switch to camera, and the audio is spiking, so I'm guessing it works. I will sit down. I'm still close to the camera, so you should be able to hear me. If anybody is listening, if you want to ask some questions, you are free to, you can do that in the comments in the right section. We had 2 lectures yesterday and the day before that. If you want to look at that, there are links on my on my YouTube channel. Also, you have links how to support this channel in my description down below this video, so if you want to check that out as well. And let's start with this one. Celestial sphere is something that we did on the first day, and I only did one example, so I'm presuming that it's not going to be sufficient for you to completely capture the celestial sphere situation. So in one of my next videos, I'm going to draw a couple of these with different numbers as a form of practice. But today I'm going to focus on trigonometry. I'm going to focus on a triangle. Specifically, I'm going to focus on this triangle that is taken from this sphere. So I have 3 points. I have a point that is directly above my head, above the head of the observer. That's zenith. That's this one here. Then I have one of the poles, closest poles to this one of the closest poles to my position, either north or south. And then I have, so that I have this, and then I have the line connecting my horizon and the line of the star. So I have that line. So this is the triangle. This triangle here is I'm focusing on. So basically we have a triangle here, and once you have a triangle, we have trigonometry. So triangle is directly connected to trigonometry. This triangle consists out of 3 sides and 3 angles, 3 corners in the side. So let's review one more time. What do we have? We have equator line. So this is equator line, and then I have a star that is here, and this line is declination, and then somewhere on the top of this I have pole north. So from the equator to the pole I have 19 degrees, so that means this is 19 minus declination. And then I have my horizon somewhere around here. Let's get the blue one out. So I'm going to draw a horizon. I'm going to draw it like this, something like this. And then I have observer somewhere here, and then I have zenith. So this is a point directly above my head that is at 90 degrees to the horizon, and from the horizon towards the star I have a height, and that means this leftover is 19 degrees minus height. So from horizon to zenith is 90 degrees, from here to here, from horizon to the star is height, and from the star to zenith is the leftover of the 90 degrees, so 90 degrees minus height. And from the equator to my zenith, so from here to my zenith, this here is latitude. This is how far I am from the equator, and that means between equator and pole is 90 degrees, so the leftover is 90 degrees minus latitude. So that is how I got 3 sides of the celestial triangle. I have 90 degrees minus height, that's this one, 90 degrees minus declination, and 90 degrees minus latitude. On the horizon level, the angle I'm measuring, it's called azimuth. So that means this angle here, the angle is azimuth, and on the equator line, I'm measuring hour angle, because each 15 degrees is 1 hour, so the angle can be converted to time, and time back to angle. So this angle here is called local hour angle. This angle here is where the star is, and it's marked with letter P, and we do not use it, we do not calculate it. So what is important to know about trigonometry? When you have trigonometry, you have also trigonometry rules. You have cosine and sine rule. Now, what are cosine and sine? So if you have your calculator with you, you have here sine, cosine, tangents. You have these three functions here. So sine, cosine, and tangents. And what are they? If you draw a circle, so let's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's too big, I believe. So let's see, can I do it like this? Okay. So if you draw a circle, the diameter doesn't matter. Literally doesn't matter. This is a circle. And you make distance from here to be 1. So this is 0 and this is 1. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm missing 1, so it's smaller. So I need to cut this down a little bit. So this is 0.1, this is 0.9, and all the numbers in between. Now, let's say I need to calculate sine of 20 degrees. What is sine of 20 degrees? What is cosine of 20 degrees? That's the question. So I have an angle of 20 degrees. What are his sine and cosine values? Now, in mathematics, and this is one of the reasons why people, mariners, have problem with these calculations, because there is something different in mathematics from the way we calculate angles in navigation. In navigation, this is R0, this is R0, north is R0, and then you have 90, 180, 270, 360. That's navigation. That is how you measure angles in navigation on compass. In mathematics, the ground level, so like this is 0 degrees. This is 0 degrees, and the angles are measured counterclockwise. So it goes 0, 90 degrees, 180, 270, 360. So this here is actually 90 degrees in mathematics. So if I need, where's my pen? So if I need 20 degrees, that means I would put 0 here, and I would measure 20 degrees here. And this is a line of 20 degrees. This is a line of 20 degrees. Now, this line is crossing this circle in this point. In this point, I draw a straight line down here. Now, what you have now is you have this side from here to here, and you have this side that can be also read here. So we have a 90 degrees angle. So we have a 90 degrees triangle. This angle here is 20 degrees, and I have this side and this side. So this side and this side. Now the value, let me just show you that here. So this value here from here is actually cosine value, and the value of this side is actually sine. So as you can see here, cosine of 20 degrees should be something around 0.9, while the sine of this angle should be something around 0.35, 0. So this is 1, 2, 3, 35. Mathematically, you can do that by typing sine of 20 degrees equals 0.34, and cosine of 20 degrees is 0.939. So this value can be obtained by calculator. You have a calculator, you type it in. But the way they got these numbers are actually by doing this. You have this circle. It doesn't matter how big the circle is. The only thing that is important is that the diameter is labeled as 1. So 1 can be 10 centimeters, 20 centimeters, 30 centimeters, doesn't matter. You have a scale that the center is 0, the edge of the circle is 1, and then you split this on 10 identical parts. So you have 0.1, 0.2, 0.3. Then you draw a line at the desired angle, no matter what that angle is. It can be any angle between 0 to 360. And this line here that goes at 90 degrees on this line here is the sine value, and this line here is a cosine value. So cosine is actually the length of this side of the triangle, giving that this is the angle that we are looking for, and this is the right angle, and this is a sine. Now this is something that is covered in high school first year or college first year, depending what programs are you taking, or what direction or what industry you are attending. So this is a cosine and this is a sine. Now the reason why this is important is if you notice something interesting. If this is 20 degrees, how much is this angle here? So this is 20 degrees and everything is 90 degrees. So this angle here is actually 90 minus 20. So the leftover. And what that means is that for this angle, this is his sine value. But for the opposite angle, this is his cosine value. So that means sine of 20 degrees equals to cosine of 90 degrees minus 20. So let's see, is that true? So 19 minus 20 is 70. Cosine of 70 equals 0.342. This is very important in navigation, that the sine of a value is equal to cosine of that same value subtracted from 90. So that means sine of x is equal to cosine of 90 degrees minus the x. So trigonometry functions, they flip their position, because this is what we have. We have now two triangles, and they share the same size. But for this triangle, this is a cosine, and for this triangle, this is a sine. So sine of an x value equals to cosine of 90 degrees minus x. You can test this out. Put sine of any number and then write it down, and then calculate cosine of 90 degrees minus that value here, no matter what that value is, between 0 and 90. Now, this is really basic of trigonometry. You have two options. You're either looking for a side or you are looking for an angle. So two options. Either one of the sides is missing, so you know two sides but you don't know this one, you know this one but you don't know this one, so you have three sides, two you know, one you don't know. You need to calculate one. And the option number two is you have two of the angles or one of the angles and couple of sides, and the second angle is missing. Now, the basic formula in trigonometry, so no matter what the sides are, so in our case in navigation we call the sides 90 minus latitude, 90, doesn't matter, ABC, ABC, doesn't matter what the name of the sides are. The rule to get the side, So the rule to get the side is, so you are looking for side, so one of the sides, let's say A, B, C. So you are looking for B side. So B side is sine of this, the one that you are missing. So sine of A times sine of C, because I'm looking for B, plus cosine of A times cosine of C times cosine of the angle that is across the side I'm looking. So if this is B side, that means I'm looking for beta angle. So whatever angle is across the side I'm looking, that's the angle it goes onto the end. And this is basic formula in trigonometry to find one of the sides. So if you are looking for this side, it goes this times this plus this times this angle that is on the opposite side of the side that you are looking for. And this formula is the same in terrestrial navigation, in ocean navigation. You have it in stability as well, and you have it in celestial navigation, because we have triangle. The moment you have triangle, you will have this formula. You cannot skip that. So let's convert this basic formula into what we actually need. So we need height. So we are looking for height. So sine of height calculated equals, now the formula goes sine of two other sides. So sine of two other sides, so that means sine and the other side is declination times other side, sine of latitude plus cosine of declination times cosine of latitude times cosine of the angle that is opposite to height. The angle that is opposite to height is local hour angle. And that is how you get formula for one of the sides that you need to calculate. And it is all from this basic formula. So one side equals the other two sides plus the other two sides times opposite angle. So how would we get formula for declination? So let's say sine of declination. So declination is missing. So once again, we have declination here. The leftover sides are sine of latitude, sine of this side here, times sine of height, so height, plus cosine of latitude times cosine of height times cosine of the angle that is opposite to declination, and the angle that is opposite to declination is azimuth true. So that is how we get formulas for height calculated or for declination. So one of the two sides. I mentioned at the beginning, latitude is always a value that we know because we put assumed latitude. Assumed latitude is any number that we select from the globe. So any number from here. So that is why we do not extract the formula for latitude, because latitude is always a known data, known information. The only two information that could be missing is height calculated or declination. Okay, so this covers the side. What is formula for angle? So we have angle beta missing. So angle beta is missing, and now we have this. On the top, we have sine of a side that is opposite to this angle. So that would be B minus sine of the rest of the sides. So sine of BC, cosine of A, cosine of C. So formula for angle is the angle I'm looking for, sine of the side, one of three sides, that is opposite to the angle I'm looking for, minus 2 sines of the rest of the sides and 2 cosines of the rest of the sides. So this is a formula that we use to get one of the sides of the triangle, and this is the formula that we use to get angle of the triangle. So in our case, we have sine of azimuth. So we could be looking for azimuth, where the star is supposed to be, where we need to look for the star, in what direction, or any other celestial object. So, sorry, it's cosine. We're going to convert it. Now, what is opposite to azimuth? Opposite to azimuth is declination. So we have sine of declination on the top minus the remaining two sides. So sine of height times sine of latitude divided with cosine of height times cosine of latitude. So that is basic trigonometry. We have a triangle, and because it's navigation, the triangle is no longer ABC, it's actually declination, height, and latitude. Declination, height, and latitude. Another angle that could be missing is local hour angle. And the same matter as this one. So what is opposite to local hour angle? Opposite to local hour angle is height. So it goes sine of height minus sine of remaining two sides. So that would be latitude times sine of declination, cosine of latitude times cosine of declination. And these are the four main formulas we use in celestial navigation. They are basically driven from trigonometry, basic spheric trigonometry, where you have three sides and three angles. One side is always known. This one is obtained from almanac. So this one is obtained from almanac. This angle is obtained from almanac. And these two you need to calculate. So bearing and height. So we have two known sides and we have one known angle. By knowing two sides and angle, we can calculate this other. So first we calculate the other side, so the last side, and then we calculate the angle within the triangle. And this is what I'm going to tell you. This is what I told you at the beginning of this lecture today. You have two options. You can either understand this, because this is what they teach you in Maritime College first year of mathematics. This is what they showed you, or they're supposed to show you, because this is the foundation of everything that you're going to do in terrestrial and celestial navigation. Or the formulas that you will see will look like this. So this is going to be different, this is going to be different, this is going to be different, but the formula is always going to be sine of something equals sine times sine plus 3 cosines, 1, 2, 3 cosines. And the formula for angle is going to be sine on the top minus 2 sines on the top divided with cosine of the two identical numbers. So this is the foundation of trigonometry converted to celestial navigation. And I'm going to switch now to the screen to show you. This is a website where you can visualize how sine and cosine are changing. So this is the pink circle is what I drawn on my page, and this is 0. And then as I go higher, I get this triangle, and the green line represents the value of sine of that angle, and the blue line represents cosine value of that angle. And as you can see, I had 20 degrees. So if I go here to 20 degrees, I get that the value of sine is 0.34 and cosine is 0.94. So those are the same numbers I got from my paper, because that is how you calculate sine and cosine. And you see here, if you go to 70 degrees, you get the same. So this is a triangle that is for 20 degrees, and this is a triangle for 70 degrees. So practically they are the same, just facing different direction. So this converted to this. So in this case, the blue line represents cosine and it's 0.94. And in this case, the green line represents sine and it's 0.94 for 70 degrees. So cosine of a value is identical to sine of 90 degrees minus that value. You can also use this link to check the numbers to see how the numbers are changing, and you can see that for sine of 90 degrees is 1, while the cosine for 90 degrees is 0. And then it goes into negative, and now they are both negative, and now one is positive, one is negative. And this is a first quadrant where both are positive. This is second quadrant, third quadrant, and fourth quadrant. So remember, in mathematics, quadrants are measured differently. This is 0, and then it goes counterclockwise direction, 1, 2, 3, 4. And this is one of the reasons why I always say in high school, when children are just for the first time experiencing this level of mathematics, that the professor that is teaching mathematics and professor that is teaching terrestrial navigation, they work together so they don't collide with one another, because one is directly connected with the other. So you cannot teach terrestrial navigation and completely ignore what the person that is teaching mathematics is doing. So you should have your schedule compared, so the kids have this fluent direction of obtaining knowledge. Because if you look at this, I know for some of you this is the first time seeing this, but if you look at this, this is so straightforward. So you have an angle here, you have a 90 degrees triangle here, and whenever the line is intersecting this purple diameter of value of 1, the blue side is cosine of an angle and the green line is sine of an angle. And that is how you get the value of sine and cosine. And here on this side, you can see how cosine and sine are changing. So you have the lines and to see how to connect them. And there are plenty of resources on internet for teachers, so they can do the same way I'm using this, they can also do this. Yeah, so Stipe, let's go back to screen. So good question here. The original formula, so this is the formula, this is the end formula. The original formula goes like this. So it's not actually sine of Lha calculated. It goes like this. It goes cosine of 90 degrees minus height equals cosine of 90 degrees minus declination times cosine of 90 degrees minus latitude minus sine of everything. So instead of calculating 90 minus height, 90 minus declination, 90, what we do is we convert this into sine of height, because these two values, as you've seen earlier, they are the same. I convert this into sine of declination. I convert this into sine of latitude, because these two values are the same. So originally here formula is actually all these marks reversed. So it's not sine of A, it's actually cosine of 90 minus A. It's not sine of C, it's actually cosine of 90 minus C. But because cosine of 90 minus C is the same number as sine of C, that is why we can shorten our formula, we can compress it. Because of this connection, because the sine of A is the same value as cosine of 90 minus A. So that is why the original formula is actually cosine of that side equals cosine of the other side, cosine of the third side. But because this is equal to this, we can flip it and skip the division with 90 every time when we are calculating. So that is the reason why we do the flip. That's not the reason why we do the flip. That is why we can do the flip, because of these two numbers are the same. If this was not true, if this was not how trigonometry works, you would have this formula. You will not be able to flip these two values. But because this value is same as this one, instead of calculating cosine of 90 minus height, cosine of 90 minus latitude, we just revert that and put sine of declination, sine of latitude, sine of height. So yes, we have triangle here, but the cosine of this side, of cosine of 90 minus declination, is the same value as sine of this side here, and this side here is the actual declination. So we can either do this, cosine of this, or sine of this. It will give us the same result, but because sine of declination is easier to calculate, because we do not have to subtract it from 90, we can shorten our formula and get this. You can test that easily in the calculator. If you put sine of 20 degrees and cosine of 70 degrees, you get the same number. Perfect. And now the question here remains here. These formulas, they look too complicated, and how did that guy 200, 300 years ago actually solve this? Now, today we use calculator, giving that you know how to use calculator. So you have sine of a number, close the bracket, times sine of a number, close the bracket, equals, and stuff like that. In old days, they didn't have calculator, but what they did is they had this table, and here so what you have here is this. So 300 years ago you had a person who did this on his drawing board, sine of 1 equals, write it down, sine of 2 equals, write it down, sine of 3 equals, write it down. So he drew the circle. There's my circle here. Where did I put circle? I have a circle somewhere around here. This one. So he drew this circle, and then angle of 1 degree, measure this, write it down. 2 degree, measure this, write it down. And the end results are these books. So the person 200 years ago, when he need to solve this, what he did is, okay, I need sine of 43 degrees. And then he looks for sine of 43 degrees. So he flips the page until he finds sine of half sine. There's cosine. So you have for every value between 0 every value between 0 to 360. So what did I say? 43 degrees. So sine of 43 degrees, and write down the number. Then latitude is 52 degrees. Latitude of 52 degrees, write it down. Cosine, and then he looks for cosine, and then write it down. And the process was longer because they didn't have calculator, but they have everything here in the book. So everything that a calculator can give you, every number that you type in here and press equal, every number that you have here, you have it here in this book, pre-calculated already for you. It's just a matter of finding everything. So if you want to use this book instead of calculator, you can, but you need to bring it with you. You need to have your own book for this, because this will be ridiculous. Sorry. To copy. I mean, it's like, how many pages? It's 600 pages. So 600 A4 pages. I mean, just to have somebody to copy this for you, it will be a nightmare. So these two are the same. Everything that you have here is installed in the microchip of this device. But this is what they used before they invented this. Okay. Now, yesterday, my papers from yesterday. Yesterday, we calculated the UT time. That's the correct time that we need to enter the almanac. Then we corrected the height that we measured with sextant. Then we calculated local hour angle. So that is a local hour angle from our assumed position. And then we read the declination from the nautical almanac. And I told you yesterday that we have 2 more steps. So step number 5 is height calculated, and step number 5, so 4 and 5, is bearing. So in case we have a situation that we have a known object, it can be either star, planet, or moon. Step number 1, get UT time. Step number 2 and 3, it can be either of these two: height, true, and local hour angle. So after you get these two, the next steps are 4 and 5, height calculated and azimuth calculated. Height calculated is one of the sides, so we need to use this formula, and azimuth is calculated is one of the angles, so we need to use this formula to obtain it. So those 2 steps are the next one. So let me review the numbers that we had yesterday. The star was Menkar, so we have to calculate the height. So the way we do this is we have declination from almanac, we have latitude of our assumed position given to us, or that is the number that we picked. We have cosine of declination. Declination is from the almanac, latitude is assumed, and local hour angle is calculated by summarization of the data from the almanac. Once we have that number, so once we have height calculated, we're going to have height true and height calculated. And the step number 6 would be height true minus height calculated. Let's switch to this one so it's visible. So height true minus height calculated. Height calculated is obtained by using of this formula. These 2 values are in degrees and minutes, and the end result is going to be in minutes of height, so delta H. Now the height is measured like this, and the latitude is measured like this, so they are on the same spherical slope. So that means that 1 minute of height is equal to 1 minute of latitude, and 1 minute of latitude is equal to 1 nautical mile, and that means that 1 nautical mile is equal to 1 minute of height. So once we subtract these 2 values, height true and height calculated, what we actually get is x minutes, and that is x nautical miles. That is how far off we are from our true position. This value can be either positive or negative. If we get value, and you always have to go true minus calculated, never flip it. It goes true minus calculated. And if the result is positive, that means we need to plot the error towards the bearing in the direction of the azimuth. And if the value is negative, that means we need to move away in the opposite direction from the azimuth. Because if height true, let's plot it. We have our assumed position. So this is our assumed position. And this is the height calculated of the star. If our true position, So this is our true position 1, is actually here. As you can see, the height true is going to be larger. So if I subtract this from this, the value I'm going to get is positive. So I need to move from the assumed position in the direction of the azimuth, I see the star, for that value of nautical miles. But if the value is negative, or if my true position is actually here, then the height, as you can see here, this angle, so height true, this one here, is going to be smaller than the height calculated. And if I subtract height true from this height true from this height calculated, I'm going to get negative value, and that means I need to move from the assumed position in the same direction of bearing. So I have this assumed position, I have bearing, and if the azimuth is, let's say, this is 40 degrees, if it's plus, I move plus by the delta H value, or if it's minus, I move minus and I draw a line. So that is why it is important that you always subtract true from calculated. So true value minus calculated, because plus and minus will determine is your true position forward, closer to the star, or behind, away from the star. And the step number 7 will give us azimuth calculated. Now, why do I say azimuth calculated? Why I don't say azimuth true? This formula here, as it is, this formula here, either of these two formulas, they have a problem that these two formulas do not have. Sine of height is any number between 0 and 90, and the benefit of sine is that it goes from 0 to 90. So when I calculate this, the number I get is the actual true value. I don't have to do anything to it, because height and declination, they go from 0 to 90, and the number I'm going to get here can go between 0 and 90. But for these two values, when it comes to angles in mathematics, they only go from 0 to 180. After 180, they repeat itself. In navigation, we go from 0 to 360. These two formulas can only give me value between 0 and 180. It's not possible for these two formulas to give me a number above 180. But if I observe the star on the west side of the horizon, that means the number I got is not correct. I actually have to flip the number in order to get the correct number. So that is why in step 7 we say that we are calculating azimuth calculated, not the true one. And then we get a number, x in degrees. Are we going to subtract this? Do we need to subtract this from 360 or not? Is depending on local hour angle. I told you yesterday, if you remember, this is north, and let's say we have a star here. Local hour angle is measured in counterclockwise direction, while azimuth is measured in this direction. So that means if local hour angle is any number between 0 and 180, azimuth true cannot be between 0 and 180. It has to be between 0 and 360, because they are measured in the opposite direction. Azimuth is measured in clockwise direction, local hour angle is measured in counterclockwise direction. So in the step number 4, here is step number 3, whatever, we calculated local hour angle, and if we get local hour angle under 180, that means the azimuth we calculated is not actually true, because the number that we get is going to be under 180. In order to get azimuth true, we need to subtract it from 360. So 360 minus azimuth calculated. Now at this moment, people sometimes ask me, why do we not flip it by 180? Why 360? The reason why we do that is if you have equator and you have North Pole, and if this is where the star should be, the opposite angle to that is this one. So this is 180. So as you can see, this is not possible. So if the star is not here, it's not supposed to be here. What's supposed to be is mirror of that one. So instead of this angle, we need to get this angle. So this is 360 minus this value. This is the angle and rotation of the star when we are looking at the star. So we do not add 180 on the number that we get. We actually subtract it from 360 because this is what we need to get. It's the same. Let's say you are using this formula to get azimuth of sunset. So you can use the same formula to get azimuth on sunset. And let's say you get 40 degrees. So this is not possible, okay? So azimuth of sunset cannot be 40 degrees. This cannot be location of sun setting. This needs to be, this is sunrise. In order to get sunset, this is not location of sunset because this is not how the sun moves. This is the location of sunset. So it's 360 minus 40 degrees. So it's actually 320. So sun is rising at 40 degrees, but if you are calculating with the same formula sunset, to get the value of sunset, you subtract it from 360, and this is the angle of sunset. So it's on the opposite side. It's not on 180, but it's on the other side of the spectrum. Okay, what's next? Let's see how this looks like on one of the tasks. Okay, let's go to PDF. So we have a task here that is asking us to calculate ship's line of position by observing the known star. We have latitude and longitude of assumed position. We have the name of the star, we have the times given, and we have the height observed with sextant. We have ship's chronometer error, we have height of eye, we have sextant index error, and atmospheric pressure and temperature. Step number 1 would be to get UT, so that's the first step in calculation, and make sure that if the time crosses midnight that you adjust the date. So in this case, when we are observing the star on 28, we are on 149 degrees west, but for us is 28, for Greenwich is actually 29 because we crossed the midnight. The Greenwich has crossed the midnight. So like I explained to you on the first day, make sure that you calculate the correct time and date, not just hour and minute, but also focus on the date. Once you have that, once you have the correct time and the date, you enter Almanac and you look for that page that has date of 29/11, the year of the Almanac. And because we are observing star, we are looking under Aries. So we are looking under full hour of the UT time under spring point Aries to get Greenwich hour angle. We apply correction, we add our longitude, and we add sidereal hour angle of this specific star to get local hour angle. And local hour angle needs to be between 0 and 360. If we get it beyond 0 or beyond 360, we subtract it from 360, and if we get it negative, so under 0, we add 360. So that's the first angle that we calculate from the side of the celestial triangle. Declination is something that is given to us for the star, so we just read that from the Almanac main pages. So that's one of the sides. So at this moment in the task, we have one angle, we have latitude, so that's one of the sides, and we have another side, that's declination. After we have that, we can calculate the height through, so applying corrections from the tables. And the next step is to get height calculated by using the formula I just showed. So we have sine of latitude times sine of declination plus cosine of latitude, cosine of declination, and cosine of local hour angle. Once you have all these numbers in your calculator, so let's say you have sine of something inside the calculator times sine of something in calculator, you will get the end result. So you have some numbers depending what is on the beginning of the formula. Are you trying to calculate sine or cosine? You need to reverse the value. So if I'm calculating sine of height, that means I need to reverse that by applying shift, second function. That will be the upper left key on your keyboard, and sine. And the marking on the screen will be sine on -1. So that's reversed sine, the reverse sine of the angle to get the angle. And you press equal and you get the angle in degrees. So this is the angle in degrees. If you press the DMS button, so degrees, minutes, seconds, you will get the same value expressed in degrees and minutes. So this is in degrees and this is in degrees and minutes. Second formula is azimuth calculated. If you have the advanced calculator, if you have a newer version of calculator, here 3 buttons down from the shift button, you will have this button here, or it was going to be marked as A cross B, and you can type things on the top like this. And once you are finished with the top row, you use this as a mouse to go up or down, left and right, so you can type on the bottom. And once you are finished, press equal. In my case, okay, I got, because I put 2 identical numbers on the top, let's correct that. Let's put 63. You get some number, and once you have the number, because it's cosine, so shift cosine of a number in order to get the angle belonging to that number. So because formula for azimuth is cosine, in order to revert the value, we need to activate cosine -1 to get the value of azimuth calculated. And now, because cosine of 150 gives us minus 0.866. If we go shift cosine, we should get 150. But look what happens when we put cosine of 254. We get a value, and if we go shift cosine, we're supposed to get 254, but we're not going to get 254 because cosine only can give results up to 180 degrees. So in this situation, for our azimuth calculated, we are always going to get azimuth that is between 0 and 180 on the east side of the horizon. In case we observe the star on the west side of the horizon, we need to get azimuth true, and that is actually 360 minus that azimuth calculated. And the way we're going to know did we observe the star on east side of the horizon or west side of the horizon is by observing the value of LHA. LHA is measured across the point of west in counterclockwise direction. So that means if LHA is under 180, the star is actually on the west side of the horizon, so azimuth needs to be larger than 180. So that was formula for these two formulas. So sine of height calculated and cosine of azimuth calculated is something that we use if we know the object, if we have known object on the sky. The formulas, the second two formulas I mentioned for declination and local hour angle is when you have unknown object. So for example, you have on 19th of June, your ship is on assumed position and it is observing celestial object that is unknown, unidentified. What you have is azimuth of that unknown object, the time of observation, all the data regarding your ship, the temperature, chronometer, error, and similar. And the procedure is exactly the same. So we calculate everything in the same way as we would for a star. We just don't include the sidereal hour angle because we do not know is it a star or planet. And once we have the local hour angle, we measure declination of the object. So we calculate declination as the side. So we have sine of declination equals sine of latitude times sine of height, cosine of latitude, cosine of height, and cosine of azimuth compass. So azimuth measured from the compass. It doesn't matter for this azimuth to be true because what we are looking for here is just approximate declination. The declination that we get here by calculation is not something that we're going to use later on. This is only to identify the body that we observed. So for example, by using this formula, we got declination 73 degrees and the number is positive. If the number is positive, that means the declination is north. Object is on the north side of the hemisphere. If we got it negative, that would mean it's on south. By using the formula to get angle, we calculate local hour angle, and once again we have a rule. The formula can only gives us number between 0 and 180. If the azimuth at the beginning, if the azimuth told us that the star is 7 or planet is 7 degrees, so that means on the east side of the horizon, that means local hour angle needs to be substantially larger than 180 degrees, so it needs to be converted. So we need to go 360 minus local hour angle calculated to get local hour true. Once we have that, we convert that to sidereal hour angle because in order to identify the body from almanac, we need to have declination that is fixed, that is the distance of the object from the equator, and we need to know sidereal hour angle. How far is the object from spring point, so from point of Aries? In case of identification, after we have those two numbers, we would take almanac. So we would take almanac because unidentified object can only be either planets or stars. It cannot be sun or moon. So once we have a sidereal hour angle and declination, we look here, and there is no two stars here that will have close declination and close SHA. And when I say close, I mean in 1-2 degree. So if you find an object that has good declination but sidereal hour angle is off by a degree, that's not candidate, that's not your identified body. Both of these numbers, from the numbers that you calculated, they need to be in 1 degree or maximum 2 degree separation. But there is no star here except Bellatrix and Betelgeuse, but Bellatrix and Betelgeuse are the closest one, and they have declination close to one another, so one is 6, one is 7, but sidereal hour angle is 7 degrees apart. Bellatrix has 278 while Betelgeuse has 271, so there is no way you would mistaken Bellatrix with Betelgeuse. So it's and those two are the only ones that have the numbers close to one another because they belong to the same constellation, to the Orion. Everything else is completely different. So this number is completely different from this number for any other star. And if you cannot find a match here, so nothing is approximately good in this selection here, then that means there's a potential that the unknown object is planet. So for planet, what you do here is you check the sidereal hour angle that is written to you here on the bottom. So under all the stars, you have SHA of planets for these 3 days. So you find a planet that has close SHA, and then look here, is the declination matching? If the declination is matching and SHA is matching, that means it's the planet. And once you have identified the object, then you have to go everything from the beginning, knowing the name of the star. So you need to calculate everything once you identify the object. So that is the reason why we actually in real life we never use unknown object, because that means we need to do 2 times the calculation. First calculation to identify the object, and then the second calculation to actually calculate our position by using the data we measured for that object. Okay. Okay, what else? We have, do I have sunset? Let's see, do I have sunset here? I don't have sunset here. On sunrise I only have stars, but doesn't matter. But basically that was it for today. Tomorrow, or maybe what's the time? It's 11 o'clock. Maybe we can actually finish. I don't know. Is this too much for you? Stipe, I believe you are the only one here. Maybe Ivan is also here, but do you want to see how we plot the result, end result on the chart? Because mathematics is, I'm not going to say it's easy or it's clear, but it is just there and you have to do it. You have to take your calculator and practice. So it's not something that you can skip. Okay, so let's do the drawing. Let's do the drawing. So this PDF that you see right now on the screen, you have it on my web page. For Croatian students, you have it on Croatian language. For foreigners, I will send you the link, because the English version of this document is from my new book that is not yet published. So I'm keeping the record who received the documents, so they don't start spread on the internet until I publish officially the book and it can be paid for, and so I can have funding for my next project. So the Croatian version is already available, because the Croatian version is already published officially. So you have that on my web page, or if you cannot find it, you can ask me on email, so I can send you a link. English version is not openly available, but I will send you what you need on the email. And so after you calculate all of this, so after you did all the calculations, all the equations, you end up with 4 numbers, and I'm just going to write it down here. So the first, let's go to the top. So I have latitude of 30 degrees 25.2 minutes north, and I have longitude of 149 degrees 26.3 minutes west, and then I have star Deneb and Procyon. So I need to have 2 objects, and these 2 objects, after the calculations, I got that azimuth true for Deneb is 315 degrees 0.4, and the error in nautical miles is 7. I'm going to put 7 because this is too much. And the second one is Procyon at 100 degrees 0.8, and I'm going to put -5. It's just for the example, so let's draw it. So after we did all the calculations, after we calculated height true and height calculated, and we subtracted those 2 values, let's switch. We subtracted those 2 values, we have the error of 7 minutes, meaning 7 nautical miles, and we have for the second star error of -5 nautical miles, and we calculated the bearings 315 and 100 degrees. So how do we actually get our position? We have 2 options. We can either use blank sheet, white sheet, or we can use this one. Where is it? you can use this one. On the exam, it doesn't matter what you're going to use. You can either draw your own sheet or you can use this one. You will be given this in training center. You will get this, but in the harbor office, you need to bring your own copy of this if you want to use this. And also you should ask the master before the exam, is he okay with you using the white sheet? This is a white plotting sheet, so it's not illegal, it's just white plotting sheet. Just ask for permission before you use it, because in old days, like no old days, 3, 4, 5 years ago, they actually handed out white plotting sheet, so they didn't make you draw your own white sheet. So, but let's say the harder way, if you don't have a plotting sheet, what would you do? So the first thing is you need to make a cross. You need to draw your meridian. Let me see, do I have? Oh. I don't want to smudge my triangle, so I'm going to do it like this. I hope you can see this on the screen. And then somewhere in the middle, not exactly middle, but somewhere like here, you cross it like this. So this is latitude of my assumed position. So that means this is 30 degrees 25.2 minutes north. So this is the latitude of my assumed position, and this is my assumed position. This is meridian of my assumed position, 149, 26.3 degrees west here. Now once I have this cross, on the bottom of the page, somewhere around here, I draw a straight line. Straight line, and this line is going to be my scale for longitude. So for longitude, delta long. Everything else is not going to be measured on this line here. This line is only for long. The reason why long is like this is longitude or meridians, they split Earth on 360 equal parts. So equal parts. So if I say this part is 10 centimeters, all the other parts are 10 centimeters. No matter where you measure them, they are 10 centimeters. So that is up to you. But these values are not the same as you go higher or lower from the equator. So meridians are up to you, you decide. Latitude depends, parallels depends on how far they are from the equator. So in this case, I have 7 and 5. So the values I need to be able to plot on the screen, on the board, is 7 and 5. So I want to make sure that so every half centimeters, that I have enough room to plot this. So before I decide on the scale, I need to plot my latitude. So the way to do this is you have this line, and this is 0 here. This is 0, this first dot. I need to draw a line that is under the angle of latitude. So in my case, 30 degrees 25. So 30, 25 is 30.5. So 30 and a half. So 10, 20, 30 and a half is here. And I connect that with 0. So this angle here is actually latitude of assumed position. At 90 degrees, so 90 degrees to this line, I draw the scale. So not like this, like this. And now I can see that if I pick that every half centimeters is 1 minute, I would have 1, 2, 3, 4, 5, 6, 7, 8, and that means this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and this is latitude scale, this is height scale, and this is nautical mile scale. So everything is measured on this scale except longitude. Longitude is on this scale. So latitude, nautical mile, and height, they all depend on the angle. So 7 nautical miles when you are 30 degrees away from the equator is actually this much. If we were 60 degrees, so this far from the equator, the 7 minutes would cross here, so this would be 7 minutes of nautical mile or latitude. So the higher you go, there is more stretching of a mile on the globe. So we need 7 and 5 from this scale here. Before we can plot 7 and 5, we have two bearings. So we have star Deneb, and we see star Deneb on 315 degrees. So we use this main meridian and we rotate our triangle until that same meridian is crossing the scale on the triangle on the number that we need. And we need 315. So 315 is here. This is 315. And then I make the bearing line across the assumed position, and I write the number in the direction where the number is. So 315.4 is 4th quadrant. And then I take compass and I measure 7 nautical miles on this scale, upper scale for nautical miles. And I have two options. I can either plot it here or here. If the value of 7 is positive, I plot it towards direction of azimuth. If it was negative, I would plot it here, opposite direction from the azimuth. And now on this dot, I put my triangle at 90 degrees and I draw a straight line. And this is line belonging to star Deneb. So what that means, this is where I believe I am. This is my assumed position. And this line is the only possible curve, because this is in a greater scale of globe. This is actually portion of a curve. It's not a straight line, it's a curve that goes around the earth. This is the line where the Deneb is visible on that height I measured with sextant. No other place, not here or here or here or here, can Deneb be seen on that height. And now I repeat the procedure for Procyon. Procyon is on 100, so I rotate the triangle until I get number 100.8, so a little bit over 100, almost 101. So 0 on the assumed position or 0 on the meridian, and the number I need on that same meridian. So 100 is here. And because 100 is in 2nd quadrant, I write it here. So 100.8 degrees. The error is -5. So I take 5 nautical miles. But because it's negative, I do not plot it in direction of 100. I plot it here in the opposite direction, because -5, the error from the assumed position is negative. That means I'm more away from the star. I'm not closer to the star, as in this situation I'm far away from the star. And I need another color. There's another color, I lost red, so we're going to use this one. At 90 degrees on the azimuth line. And this Procyon. So this is the only possible line where Procyon is visible on that height I measured with sextant. And this is the only possible line where Deneb is visible on that height I measured with sextant. So that means this point here is the only possible position on Earth where star can be, those two stars can be directly seen on the heights I measured them. We have another position available, but we do not use that position because we have Earth and we have observer and we have a star here. When we are calculating our position, we're going to get this. We're going to get this point and this point here. So this is the Procyon circle and this is the Deneb circle. So we're always going to get two possible intersections of where our true position is. But the problem with the second position is the Earth is not transparent, so you cannot see the star if you are on this position, because this is the angle for the star. So if you are here, or if you are here on the opposite side of the Earth, you could see that star on those heights you measured. But the problem is, in order for you to be able to see star on the height that you measured here, the Earth needs to be transparent. You need to see through the Earth. Because everybody who's here will have, so horizon is here, horizon is here, horizon is here, horizon is here. The height to the star will be the same. But for the position on the other side of the Earth, you cannot actually see the star. So there is only one possible actual position where you can see those two stars on the height that you measured with sextant. The other possible position where you can technically get the same two values is opposite on the other side, but it's not working because the Earth is not transparent. So we neglect the other position completely. We don't care about that position. So let's go back here. The intersection, this is our true position. How do we get coordinates of this true position? So we have our latitude assumed is 30 degrees 25.2 minutes north. Our true position is higher up north, so the correction is north. So if we are here and the true position is above, that means the correction that we need to apply to get the true position is north. If the true position was here, it would be south. So you have, no matter where you are at the moment, everything that is in this direction is north, everything that is in this direction is south. So delta lat is north. We do not know how much at the moment, but we will calculate that. And also longitude is 149 degrees 26.9 minutes west. So this is west. Our true position is to the west from the meridian. We have east and west. This is westerly. So the correction that we need to apply is going to be west. So delta long is west in order to get longitude true. This is assumed. And now we need to measure from here to here. So this is the difference between two meridians, our meridian assumed and our true meridian. Because this is longitude, we measure this on the scale of longitude. So this is the only thing that we measure on the scale of longitude, and it's 4.7. So 4.7 minutes west on the west side. And this here is latitude. So difference between two parallels is latitude, and this we read from the latitude scale. So that is exactly 6. So that means our true position is 30 degrees 31.2 north, and this is 9 plus 7 is 6, 4 plus 6 is 11, and that's 149 degree 31.6 west. If you want to be more precise with this, you can also transfer this here and here, and then read the value of your position. And that would be the end of the task if the task is asking you to find your true position on the white chart by observing two objects. It can be either two stars or planet and a star, or that's it. Everything else is a running fix. Or moon, you can have moon as well as one of the options. So planets, stars, and moon, this is for them. What else is important here? How would you do this here? So same thing. The center of the diagram is assumed position. And the scale here, instead of you drawing the line, you have already the angles here. So you can just connect. Basically, the point of this diagram is that you don't need this. You can actually use a plotter because you have degrees on the edge. So if I ignore the numbers on the triangle and I need 70 degrees, I just connect the cross with 70 degrees here labeled on the edge of the diagram. So I can use ordinary ruler, or I can use plotter on this white sheet because I have 360. I have a rows. Basically, I have a compass rows on the edge of the plotting sheet. And here I have angles from 0 to 90. So basically, I do not need to use this one. I can only use a ruler on the white plotting sheet. That's the benefit of plotting sheet. Okay. What else? What else is important here? No, that's it. Do you have any questions about this? Latitude assumed, or here. This is just practice. This is just, you take a couple of tasks and practice drawing. Also, when you're drawing this, it's good to use technical pen, not ordinary pen, because with ordinary pen you need to sharpen it all the time in order to avoid mistakes. Okay, what else do we have? That's it. The task is finished. We have UT time. We have UT time. We have correction of height. We have finding of LHJ. That is how far the object is from us. We have calculated bearing, calculated height, and those values are plotted on the white sheet. And once you plot it on the white sheet, you get your position where the two object lines intersect. So that is for the star. And just remember that everything comes down to this. Everything comes down to trigonometry because everything is a triangle. In terrestrial navigation, everything is a triangle. And the evidence of that is you have zenith, you have one of the poles, and you have an object, and you have triangle. And then in navigation on Earth, you have position 1, you have position 2, and you have one of the poles, and you have triangle. In stability, you have gravity, and when you move something on your vessel, it goes to another gravity point, and then you have metacenter, that is the point where ship is pivoting about, so it's a rotating point, and then you have, once again, you have a triangle. So all the formulas that you have in celestial, terrestrial stability, in either of navigations or ship stability, will be looking like this, will look like this, but they are not different formulas. They're always the same formulas, and there are formulas for triangle. And sometimes people ask me, how come I'm using the formula that is for a 90-degree triangle? The benefit of these formulas is that if you have a triangle that doesn't have any of the angles 90 degrees, what we do is flip it or split it into two triangles. So if I have a triangle that none of the corners is actually 90 degrees, what I do is I cut that triangle, because any triangle can be cut on two triangles where one has 90 degrees and the other one has 90 degrees. And what I do is, using this triangle, I calculate this side. Using this triangle, I calculate this side. And then when I have these two sides, I can calculate this one easily. But everything has a foundation. Everything that you calculate in either of specific subjects for mariners, or either of navigations or stability, everything has a foundation in trigonometry. But I fully understand that for some of you this is too late. Maybe this is too late for you to understand, and you just want formulas and you just want to type them in and be done with it. But I just want to explain to you that if, for example, somebody is watching this and he has 14 or 15 years and he's just starting to learn, this is what you should focus. First, you should understand this trigonometry, and once you understand trigonometry, it's going to be much easier to understand all the things that that person from terrestrial navigation and celestial navigation is going to tell you. And actually, when I was preparing for this today, I found this book. And as you can see, this is how old is this? 20 years. So this is over 20 years old. This is when I was going on a ship as a cadet, and these are my notes I took. So you will see that all my notes, you see, formulas A, B, C. So I had triangle with me all the time. I have collision regulation rules, mandatory, conversion, inch, feet, and then I have, you see, celestial sphere with all the formulas taken out from the triangle. So if you understand the triangle, it's easy to calculate whatever you are missing in the triangle. So all the formulas I have here, and this is what I brought with me every time when I went on ship. So I have see, triangle. Everything comes down to triangle. So every time I have to calculate something new, I just go back to triangle. The noon report, stability. So see, to be used for navigation. So this is something I brought. So you have everything on one place on the bridge that you can look up in case you need it. So I have tides here, how to calculate tides, everything on one spot. What to do when you are taking over the bridge, watch, and so this is something that you could make for yourself. So have a small notebook with everything that you need in order to make your duties during the watch easier. And I know that in most cases today everything comes down to paperwork, lots of paperwork, but every now and then you need to actually do something that is related to maritime training that you obtained in your school. Okay, if you have questions, I will stay here for more questions, but basically what I wanted to cover today is over. I want to show you, I know this is confusing, because usually this is something that you need to build. You need to first explain what is sine, what is cosine, what is tangent. So it takes time, and I know that if that part is not covered in school and high school properly, and then you come on maritime college or you come on these masters or officers exam where we need to know this, because this is a level of officer. This is the level of knowledge an officer needs to have. Trigonometry. This is basic trigonometry. This is not something that they teach when you are 30 years in college and you having doctorate or master's degree or something. This is basic trigonometry. So if you want to become officer and master, unfortunately, for the exam, this is what you need to know, because all the calculations in navigation, they go down to this. They go back to the triangle calculation. So if you have questions, I'll be here. I can answer anything you want. And tomorrow I'm going to go through the exam questions completely from the start to end. I'm going to go through exam questions. The exam questions are, so we have sun, we have position by 2 stars, and we have Polaris. So we have Polaris star, and what else do we have on the exam? So for you who are doing celestial navigation, this is what you have. But for everybody on the Yacht Master course, under the celestial navigation, you also have Great Circle and Ram blind sailing. So on Croatian, Loxodroma and Orthodroma. So Great Circle and Ram blind sailing. So tomorrow I'm going to cover these 3, and then Friday I'm going to cover Great Circle and Ram blind calculation on English. And that will be it for this week. If you don't have questions, or if you do have questions, I'll stay here. I'll switch to another mic. Awesome.